For today's video, I'll be making a couple unique coordination compounds from cobalt and using them to discuss the science, the history, and some modern uses of these type of compounds. The first chemical I'll be making is something called chloropentamine cobalt chloride, which is a chemical that was key in discovering the actual structure of coordination compounds. To begin making this compound, I began by dissolving 5 grams of ammonium chloride in around 20 milliliters of 32% ammonia. Once the ammonium chloride was mostly dissolved, I slowly added 10 grams of powdered cobalt chloride hexahydrate, which immediately began to form a dense orange precipitate of divalent hexamine cobalt chloride. Now, in order to properly explain what's happening here, we first need to take a quick moment to look at how complex bonds actually form. And it begins with molecules called ligands. As a quick warning, this might take a few minutes, so if you already know how ligands work and you just want to see the synthesis, feel free to skip to the time shown on screen. So to put it as simply as I can, a ligand is anything that binds to a metal atom by donating one or more of its lone pairs of electrons. The resulting bond is neither ionic nor covalent and is instead referred to as a dipolar or dative bond. Since ligands have to donate 2 electrons in order to form a dative bond, ligands are most often Lewis bases, with stronger Lewis bases forming dative bonds with greater covalent character and weaker Lewis bases forming dative bonds with greater ionic character. The ligands with greater ionic character are typically bound to a metal center through more electron-withdrawing atoms like halides or oxygen, and are considered weak ligands. Conversely, ligands that bond through less electron-withdrawing atoms like nitrogen or phosphorus are considered strong ligands. Ligands that bond through carbon, such as cyanide or carbonyl, are the strongest ligands of them all, and form the basis of organometallic chemistry. With ligands out of the way for now, let's take a moment to talk about metals. We oftentimes think of metals as being soluble in things like acids, but in reality, metals are really only soluble in other metals, most notably mercury. However, metals are electron pair acceptors, or Lewis acids, particularly when oxidized to a cationic state. This oxidation allows metals to easily form dative bonds with water, which itself is a weak ligand, and so the resulting complex is now soluble in water and other polar solvents. On the other hand, unoxidized metals will only bind to very strong ligands like the previously mentioned carbonyls. Since this dative bond is nearly covalent in character, the resulting complex can be soluble in nonpolar organic solvents. Now, even though many non-transition metals can form dative bonds, transition metals can form them particularly easily due to the fact that their outer bonding electrons exist in their rather large d orbital. If you look specifically at the electron configuration of the cobalt-2 ion, you can see that there are 3 unpaired electrons in the 3d orbital and completely empty 4s and 4p orbitals. Period 4 metals in general are the best examples to understand this concept, and so for now let's limit our discussion to these transition metals with partly filled 3d orbitals, excluding of course the posers scandium and zinc. When ligands form dative bonds to cobalt or any of the period 4 transition metals, they can form them in one of 2 ways depending on the difference in energy between the d orbitals. This is called the ligand field splitting parameter and is dictated by both the metal and the ligand. A low ligand field splitting parameter means that the energy difference between a metal's 3d and 4d orbitals is small. If this is the case, it means it'll require less energy for a ligand to form dative bonds with empty 4d orbitals relative to the energy required to pair up with existing 3d electrons. Ligands that bond to these outer orbitals maximize the number of unpaired electrons in the resulting complex, and this is called a high-spin configuration. These high-spin complexes are typically very ionic in character and therefore very liable to ligand substitution. Metals with small ligand field splitting are typically smaller atoms with lower charge states like divalent manganese, nickel, and cobalt. However, if the ligand field splitting parameter is large, it will require less energy for a ligand to first pair its electrons with the unpaired electrons in the 3d orbital before beginning to add electrons to the outer orbitals. This inner orbital hybridization minimizes the number of unpaired electrons, which is referred to as low spin. These low spin configurations are much stronger and therefore resistant to substitution. Metals with large atomic radii or greater charge states such as trivalent iron, cobalt, or chromium tend to result in larger ligand field splitting. Now at this point you might be wondering what the role of ligands are in all of this. If you remember earlier, I said that ligands that bond through more electronegative atoms are weak, while ligands that bond through less electronegative atoms are strong. This is because the electron withdrawing effect of weak ligands pulls the atomic nuclei together, therefore reducing the ligand field splitting between d orbitals. This means that weak ligands will more often hybridize to outer orbitals, resulting in high-spin, weakly held dative bonds. Strong ligands, on the other hand, increase the ligand field splitting, making them often more difficult to bond to a metal center in the first place, but much harder to remove once they have bound. Now that you hopefully have a better understanding of how transition metal bonds actually work, let's look back at the reaction. As we discussed, cobalt chloride hexahydrate is simply a complex of 6 water molecules bound to cobalt through dative bonds and bridged by 2 chloride counterions. Since water is a weak ligand and the splitting parameter for divalent cobalt is small, these water molecules are all complex to cobalt's outer orbitals. Ammonia, being a much stronger Lewis base, will easily displace the water molecules in what's called a ligand exchange reaction, forming a divalent hexamine cobalt complex. Since ammonia is also a strong ligand, it will partly bond to cobalt's inner 3d orbital, reducing the number of unpaired electrons from 3 to 1. This resulting complex is far more stable as a result, but the one unpaired electron means that substitution is still possible. Since ammonia itself is neutral like water, its ligands do not contribute to the charge of the resulting molecule the way hydroxide would, and so the resulting complex ion still has a +2 charge. As a quick side note, when used in lower aqueous concentrations, ammonia will instead act as a Bronsted-Lowry base, forming cobalt hydroxide and ammonium chloride due to the hard negative charge on hydroxide being more reactive to the nucleophilic cobalt than the lone pair of nitrogen. However, the cobalt hydroxide formed with ammonia is green rather than the pink you'd see using sodium hydroxide, which I suspect is the result of some partial coordination with ammonia. Anyway, once all the cobalt chloride hexahydrate had been added and given ample time to react, I began to add 20 milliliters of 15% hydrogen peroxide in small additions. This reaction is highly exothermic and will result in a sudden and extreme darkening of the mixture. Eventually, the precipitate will redissolve and the solution will become a distinctly purplish maroon color. What happened in this second reaction is that the peroxide oxidized the cobalt to the +3 state, which is ordinarily very unstable. However, when complexed with ammonia or another strong ligand, the new 3d6 configuration of cobalt allows additional ammonia to complex to the 3d orbital, leaving no unpaired electrons. This new configuration is thus fairly stable. However, during the oxidation, the hydrogen peroxide replaced one of the ammonia groups with a water molecule, which is the reason it turned purple. This water can be replaced with another ammonia ligand by adding more ammonium chloride and heating, which will precipitate the bright orange salt hexamine 3 cobalt chloride by subsequent cooling. Hexamine cobalt 3 chloride was used as a basis of support for the original Jorgensen-Blomstrand model of transition metal amine complexes. Under this model, a transition metal amine complex was visualized as chains of pentavalent nitrogen centers that each terminated in an anionic amine group. The charge state of the metal center under this model would dictate the number of chains, and so hexamine cobalt chloride was visualized like this. This model seemed to be accurate, as a reaction of hexamine cobalt chloride with excess silver nitrate would immediately precipitate 3 equivalents of silver chloride. However, by neutralizing the excess ammonia using hydrochloric acid and heating, you can force the coordination of a chloride ion to the inner 3d orbital in place of the water molecule, rather than having all 3 chloride ions bound to the outer 4d orbital. To do this, I simply added 37% hydrochloric acid in small additions until the resulting solution was strongly acidic. This will produce a large volume of white fumes, which is due to ammonia gas and hydrogen chloride gas reacting in the air to form ammonium chloride. I think this looks pretty cool, but it's probably best to not breathe this stuff. Once the excess ammonia was completely neutralized, a red precipitate of the barely soluble chloropentamiene cobalt chloride began to crash out. The mixture was next heated to between 55 and 65 degrees Celsius for 30 minutes to fully induce coordination of chloride directly to the 3d orbital. This was then allowed to cool, and my final product collected by vacuum filtration. The resulting chloropentamiene cobalt chloride is a violet red diamagnetic salt that I scraped onto a watch glass and allowed to dry on my desk overnight. I then weighed my final dry product for a final mass of 6.82 grams, representing a 64.8% yield. Now, what makes this salt so special isn't just its pleasant color. In the early 1900s, the inorganic chemist Alfred Werner proposed, among other things, that instead of being held together on long chains, ammonia and other ligands were bound directly and individually to a metal center. This model predicted that these inner sphere ligands would be less reactive than those bound to the outer 4d orbital, while the earlier Jorgensen-Blomstrand model would expect all bound ligands to be equally reactive. By reacting aqueous chloropentamine cobalt chloride with excess silver nitrate, only 2 equivalents of silver chloride would precipitate, which showed that the third chloride was indeed directly bound to the metal center and therefore highly resistant to substitution. This discovery, along with further experimentation with chloramine cobalt complexes, was the basis of Werner's Nobel Prize-winning model of metal complexes, and to this day it's the model we still use. Now, the second cobalt complex I'll be making today is called chloropyridine cobaloxime. This cobalt complex is a good example of how a resulting complex can be charge neutral, and will introduce a new kind of ligand. Not only this, but due to its unique structure, this chemical has been considered as a model compound for vitamin B12 for studying the properties and mechanism of action of the vitamin. As the name implies, this compound requires 3 ingredients to make: cobalt chloride, pyridine, and dimethylglyoxime. To get started, I began by dissolving 5.5 grams of dimethylglyoxime in around 200 milliliters of 95% ethanol. Even in ethanol, this stuff is only sparingly soluble, and so to get it to dissolve completely, I had to give it a minute on my hot plate. Once the dimethylglyoxime had completely dissolved, I again began to slowly add 5 grams of powdered cobalt chloride hexahydrate. The moment the cobalt chloride comes in contact with the ethanolic solution of dimethylglyoxime, it will briefly turn blue before forming a reddish-brown soluble complex. I wasn't able to find any specific literature on this intermediate, but if I had to guess, I'd expect it to have the same square planar geometry as the famous nickel-bis dimethylglyoximate. Dimethylglyoxime is a chemical that's capable of forming 2 coordination bonds to a metal center, making it what's called a bidentate ligand. Chemicals that can only form 1 coordinate bond to a metal center, such as ammonia, as well as most of the others we discussed earlier, are called monodentate ligands. Naming conventions for simple ligands are equally simple, and aside from indicating the number of ligands with the classic di, tri, tetra, penta, etc. prefix, the only other thing you may have to do is indicate whether the complex is cis or trans, if different isomers are possible. However, to avoid ambiguity with these more complex ligands that often already contain a prefix in their own name, we use a totally different naming convention. For example, if we were to complex 2 methylamine groups to a cobalt center, we would not call it a dimethylamine cobalt complex, as dimethylamine is something else entirely. Instead, we would call the complex cobalt bis methylamine. For 3 of these complex groups, we would use the prefix tris. 4 would be tetrakis, and so on and so forth. That said, the intermediate here would likely be called cobalt bis dimethylglyoximate and exist in an uncharged state due to the neutralization of cobalt's +2 charge by the partial deprotonation of dimethylgloxime. Anyway, once this has had ample time to react, I next added 4 milliliters of pyridine, which resulted in the solution changing to a somewhat green color. I'm not actually sure whether pyridine or chloride can even complex at this point, but if they can, it's not very stable. In order to stabilize this complex and fully complex the chloride and pyridine at the axial positions, the cobalt must be oxidized to the trivalent state. This is done by once again adding 15 milliliters of 20% hydrogen peroxide and allowing the complex to sit and react for a while. After about 20 minutes of reacting at room temperature, the solution was cooled on an ice bath, which crystallized the product from solution. It was then collected by vacuum filtration, dried overnight, and weighed for a final mass of 5.62 grams, representing a 66.3% yield. The big difference between this complex and my first one is that this complex is electrically neutral and much more covalent in structure. As a result, no counterions are necessary to stabilize the final complex, and so this chemical is much less soluble in water or other polar solvents. In fact, this chemical can be recrystallized from a hot mixture of ethanol and ethyl acetate, which is unusual for a metal-containing molecule. Now, for my third and final cobalt complex, I'll be making potassium hexanitrocobaltate. This compound is a good example of how the choice of ligands can result in a metal complex with a negative charge rather than a positive or neutral one. And unlike the other complexes I've made today, This one is of significant commercial importance. To get started, I simply dissolved some cobalt in nitric acid. This is because when I filmed this, I was under the assumption that cobalt nitrate was necessary for the reaction, but in reality, I think any cobalt salt would work just fine. While the cobalt was busy dissolving, I next dissolved 14.2 grams of potassium nitrite in some distilled water and set it aside. I then added my now cool solution of cobalt nitrate to the potassium nitrite solution in what I assumed was a large excess of the cobalt salt. This resulted in no visible reaction, as nitrite is not a very strong ligand. However, by adding some hydrogen peroxide yet again, the ligand field splitting parameter was increased, allowing the nitrite ligands to coordinate to the inner 3D orbital. Since each of the nitrite ligands has a -1 charge and cobalt here has a +3 charge, the resulting complex will have a -3 charge, which is stabilized by 3 potassium counterions, resulting in a virtually insoluble yellow precipitate. This precipitate was collected by vacuum filtration, rinsed thoroughly, and weighed for a final mass of 12 grams, representing a 90% yield based on the initial mass of potassium nitrite. Now, what's interesting about this third complex, aside from it being the only negative one of the bunch, is that potassium hexanitrocobaltate is sold as a popular yellow pigment more commonly called Indian yellow. Given that I filmed this third reaction ages ago and could significantly streamline the procedure from how I showed it here, this complex will eventually get its own full pigment video. In the meantime, however, I figured it was silly to leave it out of a video on trivalent cobalt complexes. In any case, that's all I have for today. This video has been an example of the more educational leaning videos I mentioned I wanted to start making every so often. If this is a format you enjoyed, I'd love to hear about it in the comments, and if you didn't, I'd equally appreciate any critique. Regardless, I hope you found this interesting, and as always, I want to thank all my incredible patrons for their generous contributions. Your support is vital and very, very appreciated. To everyone else, if you'd like to see more content like this, consider subscribing on TikTok, YouTube, Instagram, or even by becoming a patron yourself. Thank you all so much for watching, and I'll see you next time.